Welcome back, ladies and gentlemen. In this video, we'll take a review of forces. We will talk briefly about spring force, and then we'll look at another application of forces which is linked masses and pulleys. Okay, so this is a table that we've seen before. This is a bit of review of forces with the addition of spring force, which we would have spent more time with in class. You'll see this in Physics 12, so it's one that we should mention here. Okay, so first of all, gravity, friction, normal, and applied force. We've seen all those before. We will get to using tension in this video when we are talking about linked masses. Okay, so before we go on to the next slide, I just want to mention a little bit about spring force. Spring force is a formula that you will see on your formula sheet. The spring force equation is Fs, which stands for spring force, is equal to Kx. K is just a spring constant. Stronger the spring, the higher the spring constant. If you think of like springs in your car suspension, those would have a very high spring constant. X is just the amount of displacement of that spring. Displacement. So if you displace a spring, it will apply a force. So if we look over in this diagram on the right side, here's a golf ball on the spring. This we would call the spring's unstretched length. Okay, then if we were to push on this spring or push this golf ball in a little bit, we've now displaced this spring. Usually we use a delta X for that. We've now displaced this spring a little bit. So that displacement is what we would use in our formula to figure out how much force that spring is applying to that golf ball. Okay, this is like a Nerf gun. You push a ball into a Nerf gun, you push the trigger, and that little spring will eject that golf ball out of the gun with the force that is, pushing it out of the gun. Okay, in the other direction, if we think of in another manner, if we think of stretching out this spring, the restoring force or the spring force that's acting on this golf ball is going to be just in the opposite direction. So I'm just commenting on this because your spring force is always going to be a force that tries to restore the spring to its original position. So if we pull this golf ball backwards, our force will be acting to the left. Our delta X that we would apply in our formula here would be shown just on our diagram there. Okay, so spring force, we're not going to look at that in great detail with a lot of questions, but I do want to mention it because it's one that's on your formula sheet. We would have covered it in class. You will see it in Physics 12, so there you go. So for today's lesson, we are going to look at more questions on linked masses. We'll get to those in a minute, but just a quick little review of some types of questions and free body diagrams that we've seen. We've done horizontal acceleration questions, like if we have an applied force being put onto a mass. Okay, we've also had vertical acceleration questions where we have, let's say, a pulling force, and let's call that tension, and we'll call this gravity. Maybe this is like our shopping bag that might break. In our horizontal acceleration question, I'm going to go back up here because we might have had a friction force, and if that friction force is smaller than our applied force, then of course we'll have an acceleration going to the right. Okay, our vertical acceleration looks like so. If we have constant velocity, that's where we have some kind of applied force that is just balancing out the friction force. Okay, where we have zero net force. So if there is no net force, there is no acceleration, which means that we have constant velocity. Okay, forces at an angle. We've looked at questions where big sister is pulling little brother in a wagon. So, we take those questions and we break those into individual components. Okay, then we looked at ramp questions where we had a block on a ramp and we'd have some portion of gravity that's pushing down the ramp. We'd have some portion of gravity that's acting perpendicular to the ramp. Okay, we also looked at projectile motion questions where the only force that's acting on a projectile is gravity, which is why we only have acceleration in the y direction. Okay, we just looked at spring force. That is just a restoring force that is caused by springs if it is stretched. Okay, and today this lesson will focus on linked masses. So linked masses, what does that mean? Before we get to that, just a quick note on tension. Tension force, if we've got two people pulling on a rope here, and we have person on the right pulling with 80 newtons of force, well, the tension in the rope that this person on the left is pulling with will also be exactly 80 newtons. And that's, of course, if they are pulling and not moving anywhere, not accelerating in either direction, right? So the tension force, you'll hear me refer to that as an internal force. And that's just the tension in that rope at any point. If we were to put a little force meter in there, would be 80 newtons in this case. Okay, so tension is it's just a force exerted by a rope, cable, chain, and it's just called the force of tension. And this was in our table earlier that we've written down before, either FT or T. Okay, I generally use big T to talk about tension when we're solving these linked mass problems. Okay, linked mass, here's what they look like. So this is like, hey, if we have masses that are linked together by a rope, let's say we have like, hey, this is mass 1, this is mass 2, and we are pulling with some applied force. Our goals are going to be to find the acceleration of the system. Our goal will also be to find the tension in the connecting rope. So this would be like a little rope that is pulling with a tension force. So the tension in this rope at any point will be the same, and that'll become important as we analyze these questions. Okay, so our steps, we are first going to be taking a free body diagram for the entire system. So you're going to see me draw things like a box around this entire system, and then be thinking about, hey, what forces are acting on that entire system? Then we will do a free body diagram. Instead of for the entire system, we will do that for just one mass. So I'm just drawing a little dotted diagram around this mass. Okay, so going forward, so here's an example. So here's an example where we have mass 1. This is a 11 kilogram mass. We've got a 14 kilogram mass as our M2, and then our pulling force is going to be 100 newtons. Okay, so our first step is going to be to draw a free body diagram for the entire system, and we're going to use external forces. So external forces just means, hey, if I think of my free body being this entire thing, what is the external forces that are pulling on that box? So our F net equals MA. In this case, we'll have our net force being, hey, it's just going to be that 100 Newton force. And in this case, our total mass that 100 Newton force is pulling, it's now more. It's now 11 plus 14 kilograms, or 25 kilograms. I might just swing this up here. So that'll be 100 newtons is equal to 25 times A, and A is going to be equal to 4 meters per second squared. Okay. In part B, we'll look at using a free body diagram for a single mass. And in this case, we can think of, well, I'm actually going to do this for both masses just to prove it to you that tension is going to be the same. If we draw a free body diagram for the 11 kilogram mass, there is going to be this tension force that's pulling on this mass. That's the force that's going to be making this thing move, right? It's going to be making this thing move. And really, when I think of that free body diagram, I'm thinking about drawing my imaginary box around this guy, and there's a free body diagram for what on that 11 kilogram mass. If I were to choose the 14 kilogram mass, which you can choose either one, because the tension force that we solve for should be the exact same in both. So I'm doing this. I'm going to solve this question for tension in for both bodies. Going forward, you don't only have to show it for one. Okay, so if we look at this one on the left, whoops, I'm going to apply my F net equals MA to both. So on the left-hand side, that just is T is equal to my mass is 11 times A. And my A, I'm just going to go and erase this because I've already solved for my acceleration that it's going to be 4 meters per second squared. So the tension in that connecting rope will be 44 newtons. Okay. For the 14 kilogram mass, if I'm applying my F net equals MA, that would be 100. And I've got this tension force pulling backwards to the left. So I'll put a negative sign in front of that. The mass is 14 kilograms. The acceleration of this thing is 4 meters per second squared. So if I do a little bit of math here, I can find that my tension is going to be 100 minus 14 times 4, which is 56. My tension will be 44 newtons. Okay, so we'll try this in the next slide. We'll try this question again, except we'll add a little bit of friction to it. Okay, so in this case, if we have friction that's being applied to this system, so in this case, we still have our 11 kgs, we still have our 14 kgs, and this is still a 100 Newton pulling force. Now, just along the bottom here, I'm gonna just kind of draw a little, like a little diagram, and that arrow, or a little arrow, sorry, and that arrow is gonna represent my friction. And friction is always an external force. So my force of friction on either one of these things is going to be my mu times normal force. And in either of these cases, our normal force is going to be equal to gravity. So my my force of friction is going to be mu times mg. So for my 11 kilogram mass, my mu times mg is going to be 0.18 times 11 times gravity. If I plug and chug that, I think we get 19.4 newtons. Okay, and if I do the same thing for the 14 kilogram mass, that force of friction will be 24.7. Whoops. 24.7 newtons. Okay, so for part A of this thing, oh, there's the big red box. Friction is an external force. So for part A, to find the acceleration of this system, my net force acting on this entire system is going to be that 100 newtons. And then I need to subtract my 2 friction forces. Okay, so subtract 24.7 minus 19.4. That's going to be equal to total mass that's being accelerated times acceleration. Okay, if we plug and chug, we should get that 25A is equal to 55.9. And then A is equal to 2.2 meters per second squared. Okay. Okay, now I'm going to go and do my free body diagram for a single body. And I'm going to do that so that I can find the tension in this thing, tension in the connecting cord. Okay, so F net equals MA for my 11 kilogram mass will be T minus 19.4 is equal to 11 times my acceleration that I solved for is 2.2. Okay, and if you go and solve for tension, you should get 44 newtons. Okay, just for fun, I'm going to show this for the 14 kilogram mass. Okay, on the 14 kilogram mass, we'll have 100 newtons pulling to the right. We'll have this force of friction of 24.7 newtons pulling to the left. So my F net equals MA. I'm going to put in some numbers and we have 100 pulling to the right, 24.7 pulling to the left. And now the mass that's being accelerated with those forces is 14 kgs times the acceleration of 2.2. And if you plug and chug for that, whoops, I forgot to put tension in here, guys. This is also going to be a tension. That tension has to be on there, and we'll end up with, I forgot to put that in my force line, sorry. So let's be minus T is equal to 14 times 2.2. Okay, so now if you plug and chug for that, you'll go and find that tension is also equal to 44 newtons. Okay, so next example, we will look at another linked mass problem that you'll see are pulleys. Okay, so for pulley examples, here we've got a 28 kilogram and a 15 kilogram mass. And just by looking at this, if you have two masses that are hanging over a pulley, which way is this thing going to accelerate? Well, it's going to accelerate this way because the 28 kilogram mass is bigger. So this force of gravity from the 28 kilogram mass, that 28 kilogram mass is going to have a force of gravity of 274.4 newtons. That's just 28 times 9.8. There's also going to be a force of gravity from this 15 kilogram mass, which would be 147. And it's like they're playing a little tug of war. Okay, so if we're looking at the acceleration for this system, we'll have F net is equal to ma. Well, the forces that are pulling externally on this system are going to be these two forces of gravity. They'll be playing a little tug of war, and I'm going to call the 274.4 force of gravity, I'm going to call that positive because it is, I know just conceptually, I know that this is going to accelerate in the clockwise direction because 28 kilograms is more mass than the 15 kilograms. Okay, so my force, my F net equals ma line will look like so. Okay, and then we can go and plug and chug, and we should find that acceleration is equal to 2.96 meters per second squared. Okay, and then if our second part here is to go and look at a free body diagram for a single mass. Okay, and I'm going to go and I'm going to look at the 28 kilogram mass. So the gravity force that's pulling on that thing is 274.4. And I'm also going to have this tension force that's pulling in the opposite direction. My F net equals ma line becomes 274.4 minus t is equal to the mass times acceleration, which I've solved for is 2.96. Okay, and then if we plug and chug for tension in this case, it should be, I got 192 newtons. Okay, so just as a check for yourself, maybe do that for the 15 kilogram mass. If you do that for the 15 kilogram mass, you're going to have a tension force that's pulling upwards. You'll have this 147 gravity force pulling downwards. And in this case, you would call tension the positive force because it is going to win that tug of war. And this it's going to be accelerating upwards. So I would call tension positive, and see if you can work through a tension calculation, and you should end up with a tension that is equal to or close to, with rounding, 192 newtons. Okay, one final example is where we have two blocks that are connected. One block is hanging. If we have this type of question, friction between the 4 kilogram mass and the table is 0.12. So the first thing I'm going to do is just draw my friction on here, which is mu times normal force. Normal force in this case will be the same as gravity. So that'll be mu times gravity, or mu times mg. Okay, and if I do the plug and chug there, we get 0.12 times 4 times gravity, or we should find that our friction force is 4.7 newtons. Okay, so if I look for the acceleration of this entire system, so I'm going to think of drawing my free body diagram. What are the external forces that are pulling here? Well, I'm going to have this force of gravity from the 7 kilogram block. That's what's going to be making this thing move, right? So 7 times 9.8 is 68.6 newtons. Now I'm going to use that in my F net equals ma. The two forces that are acting on this thing are going to be the force of gravity from the 7 kilogram mass, and then we'll also have some friction from the mass on the table that's trying to stop this thing from moving. The total mass that's being accelerated here is 7 plus 4, or 11 kilograms. So there's our force line, and if we go and plug and chug for this, we should find that acceleration is 5.8 meters per second squared. Okay, that's for part A. In part B, I'm going to flip a coin, and for which mass I want to check out for part B, and I'll say, okay, let's check out the 4 kilogram mass. So 4 kilogram mass is going to have that tension from this cord pulling it to the right. It's also going to have 4.7 newtons of friction force pulling it backwards. Okay, so my force line will be tension, or T minus 4.7 is going to be equal to the mass, which is 4, times acceleration, which I've found is 5.8. Okay, if we plug and chug that, you should get your tension force is equal to 28 newtons. Okay, and similar to before, go and try and find the tension force on this 7 kilogram mass, and just see for yourself and make sure that we do get the tension force of that 7 kilogram mass as being 28 newtons. Okay, that's it for examples. Can you please give the dynamics review worksheet a try? Thanks, ladies and gentlemen, and we'll see you again soon.